Okay, now in this video we are going to talk about the branch and bound approach to solve the 0-1 knapsack problem with the breadth-first approach. Okay, so here we showed that like the maximum bound for like at level 0 we're going to be 115, and like the total weight so far is 0, and the profit that we gained so far is equal to 0, but the bound is 115. So let's see that what if we include item 1 in our bag, or we are not including item 1 in the bag that we had. So if you remember, we had, let's also write these values here. So we had P1 equal to 40. And also the rest of the values that I've written here. So P1 to P4 and weight 1 to P4. And again, we sorted their based on the ratio of value to the weight. So here we said that if like the maximum bound will be 115, okay, and because we haven't picked any item yet, so the profit is 0, and also the weight is still 0, because we haven't picked any item yet. But now let's assume that we are picking the first item, okay, that has the value 40 and has the weight equal to 2. So if you remember that the formula we had for like seeing that what's going to be then the bound, okay, when we are choosing item number 1, and what's going to be the weight, okay, after we are choosing item 1, and what's going to be the profit. So it's easy to see that when we are picking number 1, the profit will be 40. So I'm putting P equal to 40 because I chose item number 1. And the weight, okay, that we are, let's change also again to this WE, okay, again, not to get this mistaken, but the total weight. So equal to 2, because the weight of item number 1 is equal to 2. So we have P profit so far is equal to 40 and the weight equal to 2. So based on the weight that we had, total weight gonna be the weight that we had before, so that's when we're included item number 1 plus, and we are at level, here is level 1, okay, so that was when I was equal to 0, and here is when I is equal to 1, okay, so when is I is equal to 1, that is level 1. Okay, so I'm gonna run also L equal to I, and it's equal to 1 here, plus the sigma of J equal to I plus 1 up to K minus 1 and WJ. So here K again is the level that if we add that that item K to the total weight that we have, it's gonna like go and exceed the limitation of our weight. So again, in this case, the K will be equal to 3, because if we sum up the weight that we have so far is gonna be 2, okay, plus 5 plus 10 is gonna be 17, that is bigger than the total weight that is equal to 16. So K will be equal to, let's also write it here, so K will be 3. Again, if we have these all numbers together, then we're gonna have the weight that's gonna be 2 plus this 5 that's gonna be equal to 7. Here I is equal to 1, so we'll have J equal from 2 to K minus 1, that is equal to 2. So only we have, and we're including item number 2, that's gonna be, that has the weight equal to 5. Together gonna be 7. And again, based on the formula that we had, bound will be, okay, the total profit that we had before, that is equal to 40. So I'm just skipping the formula by just writing the values. So it's going to be 40 plus, here we have the sigma of the, let's also write it for this one here. So J equal to I plus 1 and k minus 1, and for the pj, so what we can gain, okay, with all the items that are legal to pick from, then we have the total weight minus the weight that we already have, so minus the total weight we have here, and it's going to be multiplied by pk, that here is a p3 divided by weight 3. So together it's going to be 40 plus the profit of the item 2, that is equal to 30, so it's going to be 70 together, plus the total weight, that is 16, minus the total weight, that again is 9, multiplied by the P3 divided by P2 divided by W3, that's going to be again number 10. Sorry, it's going to be 5, so it's going to be here 5, okay, because we have P3 divided by W3, that is 50 divided by 10 is equal to 5. Again, together this equals to 115. So if we include item number 1, again the maximum value that we can gain, okay, the profit first of all is going to be 40, okay, so the profit is going to be 40. The weight so far we're going to be 2, and the maximum bound will be 150. Okay, now we're going to see that what's going to happen if we are not including the item 1 in our bag. Okay, let's see that what if we are not including item 1 in our bag. So that is on the right side of the tree that we are not including item number 1. So still we are at level 1. Okay, so I is equal to 1. But what is the value of k? So we said that k is the value that gonna be like the level that if I'm including the weight of that, if we are including that item, then the total weight that we are gaining gonna be more than the total legal weight. So here we are not including item number 1. Okay, so I can include item number 2, that is 5. I can include number 3, that is 10, because together it's gonna be 15, and it's still less than 16. But if I include item number 4 that has weight 5, together the total weight is gonna be 20. So k now in this case is gonna be equal to 4, because that's where my weight, the total weight that I can, the total weight will be more than 16. So in this case, I'm putting k equal to 4. So here on this one here was k equal to 3, but as you see here, now k becomes 4. And the reason again is I'm looking for a level that on that level, if I add that item on that level to the total items that I have, then the total weight, okay, will gonna be more than the weight that I can gain or I can pick. So having this k equal to 4, and because I haven't picked item number 1, okay, so because I haven't won, the profit that I have so far is equal to 0, and because I haven't picked item number 1, also the weight is 0. So it means that the bag is empty and I haven't picked up anything. So p is equal to 0 and the weight is equal to 0. So now let's see and let's calculate the total weight, total W and the bound for this node that I have here. So if you remember, we said that the total weight is equal to weight that I had before, that here this WE that is equal to 0, okay, because I haven't picked anything yet, plus the sigma of j equal to I plus 1 up to k minus 1, because we are not including item number k, okay, because it's gonna go exceed our weight limitation, and weight of j, that in this case is gonna be just ignore 0 because it's, and we have j equal to 2 to 3 of wj. So it's gonna be item number 2 and item number 3. There together we'll have 15. So 15 gonna be our total weight that we can have here. Now we're gonna calculate the bound. So the bound was equal to the profit so far I have that is equal to 0. Okay, I don't have any profit yet. And I'm gonna have the, again, j equal to I plus 1. So how much I can gain from here. I'm gonna just write k minus 1 that is equal to b 3. Okay, and p of j plus the total, like like my maximum weight that I can have, minus total w, multiplied by p and location p of 4 divided by p by w4. So together pj location 2 to 3, they're gonna be 30 plus 50, that's gonna be 80. Okay, because j goes from 2 to 3, so it's gonna be 30 plus 50, together is gonna be 80. Then I will have the total weight that I can gain is 16 minus the total weight that I calculate here, that is 15, and multiplied by p4 divided by w4, that is equal to 2. So together these gonna sum up to number 82. So now let's write what we have here. I will have at level here, the profit that I had before was 0. Okay, and then also the weight was 0. But the maximum bound that I can get is equal to 82. Okay, so let's see what we have here. If I include item number 1, the maximum bound that I can get is 115. If I do not include item number 1, the maximum bound that I can gain is 82. Or $82, it's the unit that we have for the values. Okay, $115 and $82. So as you see, like if I continue on the left one, okay, I will gain more. But the breadth first approach says that, so we calculated including item number 1 and not including item number 1. So the next step will be on the left item. Okay, so as you remember, what's going to be the breadth first that we had is starting with the root, going to the left child, then going to the right child, then going back to the left child and starting again from the left child. Okay, then going to its right child, and then going to the right child of the root, left child, and then right child, then going back again here that we had for the left child of this one. So we are going row by row. So that's where the rule for the breadth first search. Okay. So we are gonna talk about now about the algorithm. I'm gonna show you the algorithm of the breadth first branch and bound knapsack. So we're gonna see that the thing that we discussed with this example, how we can implement it using the pseudocode. Okay, let's look at the breadth first branch and bound knapsack problem algorithm for solving this problem. So at first, as you remember, we said that we are initializing all the values that we have equal to 0. So, and the v here in this case is the root that we don't have any item picked yet. So the level is 0, weight is 0, and the value that we have so far is equal to 0, and the maximum value that also we can gain is equal to 0. So we are also, as you remember, the breadth first was we were using a queue for doing that. So we are enqueuing and dequeuing the nodes into a queue for actually implementing a breadth first. So that wasn't a recursive function to do the breadth first. Indeed, we were using a queue. So here we are enqueuing the node v, that is the empty the empty tree, okay, to this empty tree that we have. So while the tree is not empty, the queue is not empty, we are dequeuing the item that we have, that is item at level 0. So, and let's say that this was v. And let's say we have another item, okay, that is the next level that is equal to, that's the next level that's called U. Okay, so the item at location, the next level will be called U. So here, let's say that we are going to include the item at location U. Okay, so if we're going to include that, so the level will be increased, so it's going to be level +1. And also we're including the weight of that node or that item. Okay, remember that we included the item, the weight of the item number 1 to the total weight that we had picked up so far. And also the value or the profit that we had before with the profit that we can gain by including this item. So that's when we are including this one. Now we are checking if this weight, like the weight of this item that we're going to include, if this is less than the total weight that we can take, and also the value that we have so far, that the value is that it's going to give us going to be greater than the max value that we already have so far, that here at first it was 0, okay, because we haven't gained anything. Then, okay, so update the max value. So it's going to update the max value that we can gain. Then it checks that if it checks the max, the bound that we can gain by including the U. If this is greater than the max value, then we are enqueuing this node into the tree. Okay, so I like to see that where we can find this final solution. And again, this is the bound. Okay, so that's not exactly what we can gain. So the value that we can gain, the maximum value is defined in the max value variable. The other one, so we are also enqueuing that one. If we are not including that item, okay, the item U in the bag that we have, so we are saying that U.weight, okay, at node U, so I think you need to fix this one. So if you are not including the item at node U, okay, so what we'll have is that no change on the weight that we have so far, and also no change on the value. So that's why here, if we are not including the item at node U, there's nothing, no plus here. If you see here, if we're adding the item at location at the node U to the weight and to the value that we gained so far. So this is for not including, this is when we are including. Then here we are gonna again check the bound that we can gain. Okay, we're continuing with this node with the weight and also the profit that we gained so far, and then we are enqueuing that. Okay, so it means that if we can gain better values compared to the node that we have, then we are enqueuing that. And at the end, we are returning the max value. That's going to be how much we can gain. And as you see here, we only have this U.level equal to V.level +1 only once. Okay, because no matter that if you're including item at node U or not including that, okay, still you need to increase the level. So you are going to the next level, that is picking another item. Okay, so do you remember that we had, if we are not picking item number 1, so we can pick item number 2 that has the highest ratio after item number 1. Now let's take a look at the bound function and see how it works. Okay, so similar what we based on the definition of the total weight and also the bound. So this result, the variable result here, is equal to the bound that we defined before. Okay, so the total weight is gonna be the weight that we had before. Okay, so the weight that we had before plus the values that we can add up to the item, that if you're adding that item, then it's gonna exceed our limitation of this W that we have here. So that's the check that we are doing here. So while J is the item at location J is less than N, and N is the total item, the total number of item that we have. So if the total weight that we gained so far plus this new item, okay, that at location J, its weight, is less than the total value or error limitation, okay, then add this to the total weight. And at the end also we have that bound that were like the profit that we had before. Okay, the profit that we had before, that here is, we have this one, that u at u value, that is the profit at location u. Okay, so at node u, what's gonna be our value? Okay, what we gained so far. So we are adding the new what we had before plus these items that we calculated, and then returning these items, summing these numbers together and returning them as the bound. Okay, so that's how we can solve the knapsack problem, okay, using the breadth first branch and bound. Okay, so again, just I'd like to summarize what we did, what we said. So as you remember, we said that we have the breadth first approach uses a queue for enqueuing and dequeuing for traversing a tree, okay, in the breadth first approach. So having that enqueue and dequeue similar to what we had before, now we're going to see that how we can include or not include an item. So if we are including an item, so we are including its weight and profit that we can gain to the node that we are already in. If this node is, okay, somehow promising, and this bound, okay, does the promising task for us. So this is the similarity between this bound function and the promising function. So if this node is promising, okay, then enqueue that node. And again, we are going to see that what if we are not including that node, okay, to the to our bag. So what's going to happen on that case, and what's going to be the gain that we can have totally. So that's going to be the code for that. Then again, we are checking if the node is promising. We are enqueuing that node in the item like u, and we're continuing calling this going to this while loop that we have. And as you see here, this is not recursive. Okay, the depth first approach was recursive, okay, that we had in backtracking, but here we have the breadth first that uses a queue and a dequeuing and enqueuing for solving the problem.